Hello, my name is Chaudhry Abdulrahman, and I'd be presenting my work on GPU computing and how memory and architecture of GPU plays a role in that. The primary goal of my research under Professor David Bundy was to create coursework for undergrad students. So parallel computing is basically fetching a broken down problem into multiple processors at the same time so that it can be executed simultaneously. Single instruction, multiple data is a class of parallel computing. I work with GPUs. GPUs or graphic processing units have thousands of smaller cores which are linked together, and they require single instruction, multiple data execution. I use CUDA, which is a parallel computing platform, which allows you to run part of your code on GPU. It has threads which you can use to break down your problem. I also use Google Colab, which is an interactive computing environment, which runs Jupyter. This gave me easy access to GPUs. So my first assignment was a cool and interesting assignment. I basically convert an image to an oil painting. I got the code from an open source internet web page, uh, and then I converted it into CUDA code so that I can run it on GPU. This is a good example of a problem that can be run on GPUs because you perform the same operation on all the pixels, so single instruction and multiple data. Next up, I did matrix multiplication. A reason for that is because it has wide application in CS, in machine learning, deep learning, artificial intelligence, and image processing. And it also is a good example of a problem that can be parallelized. So in my naive multiplication implementation, I give each thread a row and a column, and it iterates through that row and column to compute just one final element. So one thread would do just one final element. As you can see, this is the code for my matrix multiplication that runs on GPU. Here I assign row and column, then I iterate through those rows and column uh, and compute the final element. So for my improved version, I'd have to go through the memory architecture of CUDA machines. We have a thing called shared memory, which has roughly 100 times low latency than global memory. Uh, you can use it as a user managed cache for better performance. So in my improved version, I use tiles or chunks of data, and I loaded them like from both the matrices into my shared memory. And then I'd use that data multiple times before moving on to next tile. This significantly cuts down my access time of global memory, hence improves the performance. As you can see here in the dark purple one, these are the chunks that are loaded in shared memory. And I access, like I using the same chunks, I basically compute multiple elements of the final matrix. This is my code for that. It's way more complicated, obviously. And here I start with shared memory, and then instead of element by element, I move tile by tile. And on each tile, I perform multiple operations. These are my performance results. And as you can see, I got a significant improvement almost with all the matrix sizes and with like almost all the GPUs. There's one specific GPU that I would like to point your attention to. It's Tesla T4. The reason for why we didn't see a significant improvement in T4 is because of the new Turing architecture. It has like a combined L1 and shared memory, so it essentially does the caching, like improved caching part for you. So even though if you do manually, you see some improvement, but it also does most of it on its own. I'm really proud of this research because it not only it helped me clear my understanding of parallel computing and all that, and like memory hierarchy in GPUs. Um, I hope it would do the same for many students in the future. I've also attached a link of the module in the video. Thank you.